Welcome back. Today we're going to take a look at setting up a mesh for conjugate heat transfer, CHT. Going to use a electronics component board with some components and look at the steps required to get a conformal or watertight mesh. One of the issues with conjugate heat transfer is quite often the geometry is just packaged loosely. It's not exactly aligned. Components are interpenetrating and they're just basically in the right place. So we'll be using an Ennova shrink wrapper to quickly make a surface mesh, which we can then divide up, which will be dividing up into all the volumes for the conjugate heat transfer. Keep in mind that not only do we need the computational domain on the outside where the air is, we also want all the components all individually meshed, and we want the surface connections between the components and the components in the volume mesh to all be conformal. I want the mesh to be the same, to line up. So let's start off by, I've got an Ennova running. Let's start off by loading up a little step file here of an electronic component or set of components. And you can see that we have, this is actually a digital display, but you can see we've got some power, some capacitors, transistors, and a liquid crystal display. So the first thing I'll do is we just take a look at what we get. It's actually made up of 30 components. So what I'm going to do, and we're not sure whether those components are going to be our computational volumes for each individual bit that's going to be meshed. So the first thing I'm going to do is just remove that, delete the volume, so we just have a group of surfaces here. And we're going to have Ennova figure out all the various computational volumes that we need. So obviously we need a computational domain. I'm going to do that just simply by creating a box here, and I'm just going to extend it out a little bit just so we can see what's going. And you can imagine this is some sort of case, and we can keep it on the sides, but we just want to have some sort of case for our test. And I'll call this case just so we can see. So now I've got like maybe it's a box that the electronics are packaged in. And maybe I've got some boundary condition here. I'm just going to do an inlet and do an outlet. Obviously this could be more detailed if you have the details, but for today this is going to show a point. And I'll just move that to make that outlet. There we go. So you can see now what I've got. Zoom in here. I've got my case, I've got my inlet and my outlet. So we're going to have air coming in through here, blowing, going over it and exiting heat. And the task is to use the solver. At this point we're not going to make any decision about what solver we're going to use. We're just going to create a valid mesh to do the conjugate heat transfer of all these components. So the way we do that, this model looks like it's in inches. I'm going to say my maximum size mesh is 0.2 inches. My minimum size mesh, I'm just going to allow it to go to 0.02. Leave the surface refinement the way it is. I'm going to be doing a shrink wrap and go first nth. And although there's some small components in there, I'm just going to look for the top 15 components. So those are the big ones that are going to cause the airflow and, the heat sinks and bits and pieces. So I'm just going to look for 15. If you want to look for all 30, that's fine. But for this test, I'm just going to look for the top 15. And I'm going to look for closed volumes. I'm going to assume there's no paper thin shells anywhere, so we can turn it off. So now we can ask Ennova to go find all the watertight volumes, all the components in this model using the shrink wrapper. And we do this here. You can see, got my mouse over this command up here, shrink wrap, press the shrink wrap. We can actually watch what Ennova's doing by turning on the messages here. And you can see it does that fairly quickly. Take a look at what it's done. Collapse lower levels. See, it's found 15 volumes. If we turn off the volume mesh and we turn off the surface groups, we can just walk through it here. Here we've got these little components here, the various components making up the bigger components of the model, and you can see each individual component, the top 15 in that model, and that's the surface mesh. Now for a CFD analysis, we want a nice smooth mesh for analysis. We don't want to have these large elements, these 2-to-1, and so with Ennova we can use this command here, which is the remesher, and you can watch what it does. So now we've got like a more computational smooth mesh. The elements get smaller, in a more controlled fashion. Now if I turn off the case and turn off the inlet and the outlet, you can see now it looks more like something that we would expect for a CFD analysis. So now, if just draw your attention to the tree here, these are our 15 volumes. So these are our 15 computational volumes. The largest volume, of course, is the air volume, and then the other 14 are going to be the actual components themselves. So for a conjugate heat transfer, not only do we want to mesh this air volume, we also want to mesh all these components because they become part of the analysis. They're the parts that are generating the heat that we want to cool with the airflow. So because it's an aerodynamic analysis, we need to put some, we're going to have a boundary layer growing on all these. We need a special type of element, a boundary layer type element for the solver to capture that boundary layer. So we can do that. So the first thing that we need to do to set up the volume mesh now we've got our surface mesh and our volumes all defined, is we need to transfer this volume information over to our geometry. So our geometry is going to be where we're going to be applying the CFD boundary conditions from. So we can do this with, watch what happens when I do mesh to geometry here. So now at a geometry level, you can now see that we have got all these individual components, volumes, all nice and organized at the geometry. And this is where we will, later on, if we go out to open foam conjugate heat transfer, this is where we'll apply all the boundary conditions to. The next thing is to finish off the volume mesh. You can do that from the global controls. So I'm just going to do 5 prism layers, and I'm going to have the first height around, say, 0.0025 inches. And those are the global. So we'll have a look at what that does in a second. And we also need to tell Ennova where all the surfaces in our model, which ones we want to grow prism layers on, which ones are going to be the boundary layers important to us. So do that with this local control. We can say we're going to work in volume 1 because that's the airflow, that's what we're interested in. I'll select that volume. I don't want to have any boundary layer on the case. I'm going to put like some sort of inviscid symmetry plane condition on the case. Inlet is just an inlet. Definitely we're going to have the low battery assembly 1. And so I can turn on the prisms by saying use volume and turn OK. And I can also now step through the rest of them here. All these need to have their prism layers on. I can pick up all of them at once and go apply parameters. So if you're dealing with a lot of parametric models and you bring a lot of geometry the same, we also have this ability here with the open mesh parameter settings to look at what we've just done on the spreadsheet. You can see here's all my surface groups, my different components, and you can see here's the prism control, use volume. And if we look at all the other volumes, you can see it's all turned off. So if I right mouse click in here, you can actually see I can export to StXL, I can save it as an Excel file. So quite often when we're doing multiple runs, it's nice to have all this saved off and just bring it in, especially if we're going to script it later. since we're talking about scripting, the most popular way to script Ennova is through Python. We also have our own internal Java-based language, but the trend now, so everything command that we see here on the GUI can also be activated through a Python command externally as well. So setting up the volume mesh, that's this little triangle here. I'm going to go out to a polyhedral mesh. Polyhedral mesh is quite useful for these types of flows and the solvers for analyzing these flows, especially if you're going to open foam. But first of all, let's just do the inflation of the prism layers that we just set up. Hitting that here. And hopefully that won't take it up. There it is back. And you can see, I didn't ask it to grow any prisms on the case, and you can see that it's inflated prisms and slid them along the case here. And we'll take a slice through the mesh in a little bit and have a look at that. And any time on the mesh, we can check its quality. We can also check if things are surface intersecting, and you can see everything is fine. That's what this little diagnostics button is. So far we're very happy and comfortable with our mesh. And then the final, excuse me, the final step is to create a volume mesh. So we'll do that here. It shouldn't take too long. You can see it's doing a smoothing step. So the way the volume mesh does first is that a tetra mesh is filled in into the volume, and then that tetra mesh is then reconverted into a polyhedral mesh. Polyhedral mesh kind of looks like, you know, what a bee would make in a beehive, and it's that octagon type mesh or that you see. So now you'll see, here we go, very, very pretty mesh. And now we can take a look at what we've done. I can collapse the lower levels. Here's our 15 volume meshes, and these are so this is the final mesh that's going to go out to our Conjugate heat transfer solver. If I right mouse button on this, I can hide the volume mesh, hide the surface mesh groups. Step through what we did last time and take a look at the surface mesh. The volume mesh, of course, is in the air that you can't see, so it's kind of a cube, so it's difficult to see. And turn on the make sure we there we go. Let me hide the volume mesh, and I'll just pick up the surface mesh here. You can see, and turn this on. Check items, and then turn off the largest volume here. Turn off the case, and the inlet, and the outlet. So that's our final volume, our final mesh. Looks like some beehive type mesh that we're used to seeing, and we can take a slice through the center of it just to show you that there is a volume mesh there, of course. And you can see that's what we end up with. And here's our prism mesh, and these are used to capture not just the momentum boundary layer, but also the thermal boundary layer as well. They're important. So, and the relationship on the momentum and the thermal, of course, is governed by the Prandtl number. So, for your particular case, you can do some hand calculations to figure out just how big you want this boundary layer to be and how many layers you want it to grow to. So that's a really quick look at the Ennova conjugate heat transfer meshing. One last thing we can do, just very, very quickly, is if I turn the mesh off, you can see that each of those components that we had in the model, they're individually meshed as well. And that's the key difficult part with conjugate heat transfer problems, is that when the mesh geometry comes in, it's packaged, it doesn't quite align properly, you have little gaps, you have geometry not quite right. You want to have everything all connected up and watertight and ship shape, and that's what Ennova does for you very efficiently. And in a normal electronics component, this is very scalable. We regularly do thousands of components. So today we've only just looked at 15 to 20, but there's no limit to the amount of components that you can have. Thank you.